Okay, so we're going to start with chapter 14, and I've been going over this so many times. What I'm going to do right now, I won't tell any extra stories. Okay, this chapter is about chemical kinetics. Kinetics talks about the rate, and the rate is another term for the speed of the reaction. It's important in chemistry for us to know what chemical kinetics is. We're told here it's the study of the factors that affect the rate of chemical reactions, such as temperature. Temperature is one of the many factors that influences the rate of the reaction. We're told the rate of the reaction is a measure of how fast a reaction makes products or uses reactants. There are two main ways you can figure out or calculate the rate of the reaction. You can figure out how fast the reaction makes products, and you can use that to figure out the rate of the reaction, or you can figure out how fast the reaction uses up reactants, and you can use that value to figure out the rate of the reaction. Either one will give you the same rate as long as the reaction is the same. Okay? It's important for us to have the ability to control the speed of the chemical reaction. That is important. Sometimes the manufacturer wants the reaction to be done quickly because time is of the essence. For example, at some point in the um, synthesis of the vaccination, there was a chemical process. So if time is of the essence, like people really need that vaccination, they will make sure that they're doing the chemical reactions speedily, right? Fast. So you want to know what factors can influence the reaction to make sure you get the reaction fast or the product fast, right? Sometimes the quality of the product matters, and in that case, you want to make sure the reaction goes slow, takes its time so you can get a good quality product. In that case, you want to know what you can do to slow down the reaction to influence the quality of the reaction. So what we're looking at here is what makes the reaction go fast, what makes it go slow. We're not judging the quality of the reactant. Sadly, in this chapter here, we won't look at that. But those of you going off to organic chemistry, you will get to judge the quality of the reactant based on the condition of the reaction. So if you're going over to organic chemistry, make sure you really understand this chapter. You will need it in organic, okay? Because it most likely will not be covered again. Okay, besides learning about how to make a reaction fast or slow it down, the next thing we're going to be looking at is the factors um, that influence the reaction, which have to do with reaction mechanism. So reaction mechanism influences the chemical reaction. So we're going to be learning the reaction mechanism, which is play by play of the reaction, the different steps. So even though we think reactions occur in one step, we will learn that the reality is even the quote unquote one step reactions occur in many steps. So as we look at those many step reactions, the reaction mechanism, we can see which part to tweak to influence the overall rate of the reaction. So hopefully you get the gist of it. We are trying to make the reaction go faster. For the most part, our goal is speed, right? So then we start here with this slide looking at factors that in general affect the rate of the reaction. So for the most part, what we are learning is the general trend and the general expectation or observations. Now, with chemistry, even though we are going through generalizing, that's kind of like stereotyping, right? And stereotypes occur most of the time with the chemicals, but you have the chemicals that do not obey the stereotype or generalization. So you want to be aware of that. Just because we're learning it doesn't mean that the chemical will fall in that category, okay? So number one, generally, most of the time, not 100%, the greater the concentration of the reactant molecules, the faster the reaction. So for most chemical reactions, when you go into the chemical reaction or you go into the lab to do the experiment, you can have this expectation, okay, this hypothesis based on experience that if you increase the concentration of the reactant, it will make the reaction go fast. But since the term generally is used here, that means about 98%, maybe 90, I don't know, maybe 85. It doesn't mean all the time, it just means most of the time, okay? When we're looking at concentration, concentration goes with solutions or liquids. But if you're dealing with a gas, since gases don't really have concentrations, for gases in the place of concentration, we'll deal with pressure. The higher pressure goes with gas, right? So for gas, we'll say higher pressure, while for solutions, we'll say higher concentration. Okay, we're told here increasing temperature increases the reaction rate for most reactions. Now you have that term, right? So I'm highlighting those important terms they use in chemistry, kind of like a cover me term, right? As they use this generally. That way when you face the exception and you go back and say, wait a minute, I thought you said all the time. They'll say, no, we said generally. That means most of the time, but not all the time. And this term here, most, same idea. For most reactions, when you increase the temperature, the reaction goes faster. That means there's some reactions for which this is not true. And then we're told here, increasing the surface area causes an increase in the rate of the reaction. This happens often, right? If you increase the surface area, now the chemicals don't have to go from a chunk as far as the chemical is concerned. Most of the particle sizes decrease, so the reaction, there's more contact for the reaction to take place. Contact is important in a chemical reaction. We'll see that all later on in the context of collision theory and the chemical reaction. Okay, number four, what about the physical state? We're told here, in general, gases tend to react faster than solids and, of course, than liquids. Now, the order is solids will tend to react slowly compared to liquids. Liquids are slower. Liquids and solids are slower than gases. Gases tend to react the most. And we'll see down the road looking at collision theory because gas molecules are very energetic. And gas molecules will act like they have a higher temperature, being more energetic. They're able to move around more and meet with the reacting molecule to make the reaction go faster, versus solid molecules are sedentary. They are bound in place due to these strong intermolecular forces. So it's going to be a while before they get up and move around and find their partner to react with, right? Oh, I just realized something. I think I'm probably more comfortable in this phase because I had this screen a lot bigger before and then I was making a lot of mistakes. So I'll just leave it like this. Okay, and then we have catalysts. Now, what catalysts do here is, for the most part, with the catalyst, we tend to use catalysts. Let me make sure this recording is on because sometimes I forget to Yep, it's recording. I forget to press that, and then I go through the whole lesson. I realize, oh, it's not recording. Okay, catalysts tend to speed up the reaction by changing the mechanism of the reaction. That's why we study about catalysts after studying the mechanism, right? Once you know the mechanism, then you know which part needs help. Not the whole reaction needs help. There's so many steps in the chemical reaction. Maybe the small part, maybe one small part needs help. So as a scientist, you get to select your catalyst based on the reaction type, and you know which part of the reaction needs help. Okay, so we're moving on to defining rate. Okay, this chapter, I'm going to give you a caveat right now. I'm going to be like chemists and give you a caveat. This chapter by some people is tedious because they get lost in the details. So at some point, I'll give you guys a summary of how we define rates because there isn't one way to calculate rate. There's so many different ways. So I'm going to be summarizing a lot so that you can just remember the take home lesson if worst comes to worst. Okay. So rate is how much a quantity is changing over a given period of time. This is a generic term for rate before we bring it into chemistry, right? A quantity changing over a period of time. Okay, the rate of a chemical reaction is measured in terms of how much the concentration of the reactant decreases or the product increases in a given time. So we're told here essentially, okay, let's summarize the second paragraph because this one here has to do with chemistry. We can get to the same rate. So I'm going to use the term rate to refer to rate by studying the change in concentration of the reactant over change in time. I'm pretty much going back and looking at what's written here, right? So here we're told the rate of a chemical reaction is measured in terms of how much the concentration of the reactant decreases. Okay, usually to refer to decrease or to give a count to decrease, I'm going to use the negative here. Okay, negative here just means amount decreases with time. Okay, they did say the concentration of the reactant is decreasing. So I put the negative there to say the reactant is decreasing. Okay, you can also figure out the rate by studying the product. We can look at the change in the product concentration divided by change in time or per change in time. Here we're told or the product concentration increases. So the product is actually increasing. Because it's increasing, I can put a positive in the front if I want, or I can just leave it as is since the positive is implied. Okay, so both rates of these are the same. Let me go ahead and add a term here or add a page because I feel like I'm running out of room. Oh, come on, add a page. Add a page, okay? So they're both rates. Rate equal this first one here. Let me see if I can just be not super lazy, but a little lazy. What happened to my, something changed. What's that? That used to be the scissors. It changed. Okay, anyway. So yeah, rate is equal to that, or the other rate as I drew it is equal to change in product concentration over change in time. And I say here amount increases. Okay? Remember, these are equal to each other. Equal to each other. Okay? So if you're either tracking the reactant or the product, you should get the same amount, which is the same value of rate. So the other thing I want to mention here is rate is always positive. Okay. If you've had physics, some parts of this chapter may be a little bit confusing because they use the term rate in physics also. If they didn't use it, then it won't be confusing. If they did, it might be a little bit confusing. But let's look at the context and why this is true. In a chemical reaction, we are looking at how fast the chemical reaction is. The chemical reaction never decelerates. Even if the reaction is slower, it's still proceeding. So the rate can be big to mean that the reaction is going faster, or the rate can be small to mean the reaction is going slow. But the rate is never negative, okay? So I'm saying here rate is positive. If rate is large, i.e., reaction is fast. If rate is small, this means I'm being lazy, but yeah, reaction is slow. Okay, so a small rate value just means the reaction is slow, not a negative rate value. So in chemistry, the rate is always positive, it's never negative. Okay, in physics, if a body is moving forward and its acceleration is increasing, it can decelerate. And here there is no deceleration as far as the reaction is concerned. So we have a fast rate and we have a slow rate. Okay, big rate, small rate. So hopefully that kind of helps if you were ever confusing the two. If you weren't, don't even worry about it. So let's go ahead and practice what I just said, what I just mentioned right here. We're going to be looking at the rate, the reaction rate. Okay, so it's told here this one on the left, the picture on the left, which pretty much goes from top to bottom, is a reaction with a fast rate. So the judgment has already been made. Somehow somebody looked at this and decided this is a fast rate. All we're going to do is confirm what they have seen. Okay. So over here, I'm going to start here. This reaction has a fast rate. That means the rate at which the reaction, either the reactants are being consumed or the products are being made, is fast. So what I'm going to do here, let me actually, I'm going to have to get used to this new icon here. Hold on. No, come on. Okay, let me make this a little smaller. There used to be scissors. It just changed. It must have just updated. Okay, so I'm going to copy that and put that right here. And we're going to be looking at the rate as far as the reactant is concerned. Okay, and do the same thing and look at the rate, oops, for this part here. The second one, we're going to be studying the product. Okay. And now I'll be looking at this down here, paste image. Okay. So with this first one here, okay. Come on. Okay, I'm trying to get used to this. Okay. This thing has, they changed the sensitivity. So I'm selecting it, but it's not responding to, hold on. Come on. Okay, let me see if I can just increase this from here. Maybe it's my pencil. Something is happening to where it's not responding to the pencil. Okay, hold on. Come on. Okay. Yeah, this is such a huge problem for me right now. Okay, let me just go ahead and do the first part because this is just a distraction. Okay, so what I'm going to do here is I'm going to track A, B, and C. One of the things I want you guys to learn how to do is when you're given a picture like this, you want to know how to handle it. Okay, so in general, I've seen in general that when you have a picture that has particles like this, go ahead and track it. Usually spend the time to track the changing amounts will give you an idea of what is being discussed, right? In the beginning, we have A, we have B. A is the blue tablet looking structures, right? And then B, a reactant. B is the red spheres, also a reactant, right? Because it's in the left of the chemical reaction. And then C is a product. So we expect, based on what we told, reactant concentrations will decrease. That is what they mentioned to us at some point, right? That's the expectation. We're going into this with some expectations. Okay. We also know product concentrations will increase. So we're not walking in here having zero expectations, not in the world of science. You walk in there with your hypotheses and you're ready to change them as it fits, right? So we're going to count. And what I'm going to do here is count and then mark this off as I'm counting. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 A's in this picture. Here I have 1, 2, 3, 4. I have 4 A's. And then here I have 1, 2, 2 A's. And then here I have 0 A's. Okay, so we know in the first reaction, before any product gets made, because we have T is 0, right? Time is at 0. Before the reaction begins, because you usually start the time when the reaction begins, you have the maximum amount of A possible, which shows here. Oh, was I counting the wrong thing? Ah, I started counting and then I moved to the wrong thing. I kind of got distracted by that. Okay, I have to be consistent, right? And count the right thing. Ah, I hate this.